bit of an up view. All right, good morning everyone. So today we're going to be taking a look at exploring integration by trig substitution through geometric proofs. And actually I don't know if it's very bright on that video, so I think I'm going to use a different color of chalk for some of my problems. So we've been doing lots of integration by other methods, whether it's integration by parts or integration by u-substitution, and doing lots of applications with integration, such as finding volumes of revolutions or some work with physics. But this is a slightly different take, and it's going to take advantage of some of our knowledge from our grade 11 and grade 12 trig identities unit to help us to simplify expressions. I'm often asked, like, hey, wait, when am I ever going to need identities? Like, when will I ever need an identity like 1 plus tangent squared theta is equal to secant squared theta? Like, that seems like a pretty obscure identity. It relates to functions that have asymptotes. Like, how is this going to be useful in the real world? And you know, it's a great question. How is this going to be useful in the real world? It's tough to model things in the real world with tangent and secant because they're not continuous functions. So it would have to be some sort of not continuous event, like a shadow lengthening to infinity and then reappearing on another side. But it's not very often you run into that as actually being the most common application. The most common application of identities like this, or even identities like this, or lastly we'll do secant squared theta, I'll just stick with these two. But really any Pythagorean identity is going to be useful when we're talking about how we use trig substitutions. I'm going to stick with these two because I'm going to talk about two examples. This example is going to relate to the length along a quadratic, and this example is going to relate to one of our geometric proofs that we're going to go and verify. So just keep in mind these two identities are going to be important a little bit later. So before we actually get to the meat and potatoes of the note, let's just review a simple integration problem. Now, I mean, I know I said a simple integration problem, but this is the indefinite integral of 2x times the root of 1 plus x squared dx. Now, this would be an integration problem that many would just solve by inspection. Others would use a u-substitution. So let's go ahead and use a u-substitution to solve for this. So I think you can see that the most complicated portion is the portion under the radical, and the portion in front contains the derivative. So this is a classic case where u-substitution is useful. So we're going to let u equal 1 plus x squared, and then hence du is equal to 2x dx. And so we're in that nice place where we can see all of du, both components, the 2x dx, as being a part of our question. So this is going to turn to a rather simple integral for us, and because it's indefinite, we don't have to worry about limits of integration at all. So this just becomes the root of u du. And of course, the root of u can be written in as u to the power 1/2 du, which then integrates quite nicely to, remember this increases by 1, so it's going to become 3 over 2. We divide, so it becomes 2 over 3 u to the 3 over 2 plus c. But now we have to go back and substitute back in our original expression. So our original expression was u was 1 plus x squared. So our whole integral will work out to be 2 over 3, 1 plus x squared to the 3 over 2 plus c. And so don't forget your constant of integration. It's incredibly important, but arbitrary. And so we've got a really kind of a classic u-substitution case that highlights how a substitution works. You're taking a complicated expression and you're replacing it with something else that makes the actual integration a lot easier to go through. So that's going to be the idea behind a trig substitution, but it becomes much like knowing when to use a u-substitution. How do you determine when to use a trig substitution? Well, this is actually a fairly nice question to start with. So I'm going to do a couple of modifications to this problem. So I'm going to grab my eraser here and drop it and pick it up. So we'll go ahead and erase most of this question. And now this problem was not particularly challenging, but I can make it very challenging, not with this, but with this. If I erase the derivative here and we go through and try and do a u substitution, it's going to be a lot harder. Let's see what happens. So we'll try and follow that same rule. Let u equal 1 plus x squared, and then hence du is equal to 2x dx. And so then I want to solve for dx because I don't have a 2x here, so I have to replace this dx with something. So this is going to become the integral of the root of u, and dx is equal to du over 2x. So du over 2x. But wait a second. Now I've got a tough problem because I have an x in here still, and u is a function of x. And so when I can't have this x remaining. I have to come up with a way to replace it. So I guess I could try and replace it from here. So I'll take this u equals 1 plus x, and I'll just solve that for x. So I've got u minus 1 is equal to x squared, which means, well, that's equal to the root of u minus 1. So this is going to become root of u times du over the root of u minus 1. And now that's still pretty challenging because now I have two expressions containing a variable, and they're not equivalent, so I can't compare them or reduce them. I guess, I could do a little bit of a reduction here. I could reduce this to the integral of the square root in total. I'm just going to combine my numerators and denominators. U over u minus 1 du. But now I have to find a function whose derivative works out to be this. And so this is going to be pretty challenging, and I'll likely have to do a lot of guess and check. It seems like I'm not making this problem any easier. Here's where I started, and here's where I've ended. So if you're finding you didn't make the problem any easier, then chances are you didn't use the right substitution. So this substitution was incorrect. So that's what we're going to use trig substitutions for. Now what I mean by making the problem easier is getting rid of a layer of complexity. So obviously we have complexity here with the square, but we also have complexity here with the radical as well. So we're going to try to eliminate one of those layers of complexity with an appropriate substitution. So I'll go ahead and erase this because that was going down the wrong rabbit hole. Now we'll pick the right rabbit hole. So we're back to picking a substitution. And I say to myself, hey self, what does this really look like? To me, that looks like Pythagorean theorem. Anytime I look at something and go, I got a square and another square, there's probably a Pythagorean theorem relationship. And the nice part about Pythagorean theorem relationships is I can replace the sum or the difference of two squares with another square. And how that's going to be valuable is I'll be able to take then the square root of both sides. So if I had a plus b squared is equal to c squared, I should be able to replace the sum of two squares with another square, which will then allow me to get rid of that layer of complexity. And that's the whole goal of a trig substitution is we're going to replace the sum or difference of two squares with another expression that's equivalent and square so that we can remove the radical. So this is how we know we're running into a trig substitution situation. A u substitution won't work, and we see something sort of Pythagorean about the whole situation. As a hint, if it's got a circle involved, you'll probably see something with respect to the Pythagorean theorem, just in the way that we define circles. So now the question becomes, which Pythagorean identity will I use? Well, I look for a Pythagorean identity that has a structure similar to 1 plus x squared. And I say to myself, okay, 1 plus x squared looks an awful lot like 1 plus tangent squared theta, because you have a 1 and a square. And so instead of letting this thing work out this particular way, I want to try and construct something that's going to simplify nicely. Now, 1 plus tangent squared theta is equal to secant squared theta. So that's exactly that situation that I was looking to do. Combine two squares to one square so that I can unradical. Now, that means that I'm going to have to replace this x with tangent of theta. Remember, this square goes to the outside. So that's how I find my substitution. I'm going to let x equal tangent of theta. Now that I have x equal to tangent of theta, I can go ahead and just work a little bit further through this. Same way I would do with the u substitution, I'm going to take the derivative because I need to replace dx with something in terms of theta. So we'll take the derivative of both sides. So dx is equal to, now the derivative of tangent theta, if you recall, is secant squared theta. So, and don't forget d theta. So this is going to be what replaces dx, and this is going to be what replaces my radical. But I'll show all the steps in one at first. So I'm going to have the square root of 1 plus tangent squared theta, and then I'm replacing d theta, or dx, with d theta. That's secant squared theta, d theta. Now we know 1 plus tangent squared theta is equal to secant squared theta. So this will be secant squared theta times secant squared theta d theta. And I've now gotten to the spot where I've reduced that layer of complexity that I found. So previously I had a sum, and one had an exponent, and I had a radical. And now I've gotten this down to, once I remove this and this, I'm going to have secant theta times secant squared theta, which is going to be the integral of secant cubed theta d theta. So now I just need to know how to integrate secant cubed theta, and that's for another day. This would be an expression that would be very similar that you would probably do with integration by parts. So I would break this up into secant theta times, or secant squared theta, it works nicely actually, times secant theta, because the derivative of, or the integral of secant squared theta is of course tangent. We determined that one from before. So I'm not going to finish off the integration here. I just wanted to actually show the process of how we decide that we've got a trig substitution, why that trig substitution is going to work, and then the mechanics of how we substitute and simplify and get down to something that's less complicated. Up here, we had 2 function types and a composite. Down here, we have just 1 function type, so much easier to integrate at this particular point. Yeah, you still have to use by parts to get from there, unless it's an integral you've already evaluated. So let's go ahead and do the actual thing we said we were going to do, which was explore integration by trig substitution through geometric proof. So allow me to erase, and we'll start off with our geometric statement we're going to verify. This will be a throwback to grade 7 or grade 8 for you. We're going to verify that the area of a circle is equal to pi r squared. So if you watched the previous video on integration by, was it by parts? No, it was by revolutions. We found the volume of this cone using integration of a revolution. Here we're going to find the area of a circle using integration, so that we can verify that this is actually the final expression we get to. So the first thing we're going to need to do is to model a circle. So I'm going to grab my Todd Rundgren novel and draw a circle. Now it is important to recognize that a circle is obviously a relation and not a function, so we're not going to be just able to deal with this all in one swoop. We're going to have to break this circle up into 2 components. So I think it makes good sense to break this circle up as though it was very similar to our unit circle. So we're just going to put it on the x and y axis right at the origin. And why not deal with the unit circle, just to keep things easy? I mean, we don't have to. If we left it generic and didn't deal with the unit circle, then the distance from the center to the outside would be known as our radius. And the distance from the center to the outside here would also be our negative radius. So this point would be negative r, and this point out here would be r. So if we knew a function that defined this whole thing, we could find the area by integrating underneath it. We'll have to ignore the bottom half of the circle so that we can keep this as being a function, which just means instead of doing the whole thing, we're just going to integrate the top and double it. And in fact, if you notice, we could probably, instead of doing just the whole top, we could just do a quarter of it. That would be more than enough, and then multiply by 4. Hint, hint. But we're going to do the whole half circle here. So remember, your equation of a circle is x squared plus y squared equals r squared. So we need to come up with a way to define this function as a function y in terms of x. So we'll take our relation and we'll rearrange it. So we'll rearrange this relation, and it's going to become y equals r squared minus x squared, and we'll take the square root. And that way we've modeled the top of our circle, or the top hemisphere, with this function over here. Now when I took the square root, I would have a positive and a negative. The negative would model the bottom, and I said we're going to ignore that because we're going to multiply it by 2. So with what we know about integration, if I simply integrate underneath that function from negative r to positive r and multiply that by 2, I'll have the area of the circle. So the area of my circle is going to be equal to 2 times the integral from negative r to positive r of y dx. Looks like a nice simple integral, but once we start substituting in y here, we're going to see it's perhaps not as nice and simple as it was. So let's go ahead and do that substitution now. So this is the integral from negative r to positive r of r squared minus x squared dx. And now this looks like a more complicated problem. But you're saying to yourself, hey, wasn't the first 9 or 10 minutes or so of this video all simply about recognizing where we have a Pythagorean theorem situation? And yeah, it was. This is absolutely recognizing that you've got a Pythagorean theorem situation. Although it's a little trickier because we don't have a 1 here, we have another expression. So we need r squared minus x squared to be replaced with something. Because it has a minus, I'm looking at not the tangent trig substitution, but I'm going to look at either the sine or the cosine trig substitution. So let's take a look at using, I don't know, we want to compare this to 1 minus sine squared theta equal to cosine squared theta. So we've got a couple of problems here. One of the problems being that, well, we don't just have 1, we have r. So I can't just say let x equal sine theta, because then I'll still have that issue of 1s. So I actually have to do something slightly different here. But this is the form that my trig substitution is going to be in. When I see the subtraction and the x variable coming afterward, I'm using a sign substitution. If I saw addition and the x term coming afterward, I would use a tangent. If I saw the x term in front of a subtraction, I would use the secant one. And if you go back and just rewrite out all your Pythagorean identities, you'll see when it's appropriate to use which. So this is going to seem a little hairy, but let's let x equal, oh, I don't know, r sine theta. And where did the r come from? Well, this r came from the fact that I need to get rid of r squared. Let's see what happens here when I write down what x squared is. X squared is equal to now r squared sine squared theta, which means this expression underneath here is going to change very simply. I've run out of room below, so I'm going to write this next line right here. So this is my substitution work. This will be equal to 2, the integral from negative r to positive r, the square root of r squared. But now instead of writing out x squared, I'm going to write my substitution, minus r squared sine squared theta. And hopefully what you see is that I'm going to be able to common factor out an r squared from both terms and remove that r squared from the integral. Now I only did one step. I'm not quite done here because I haven't replaced dx with anything. So I've taken x and come up with a substitution for it. I still need to find dx, so I still have to derive. So dx is equal to now the derivative of sine is cosine, so this is going to be r cosine theta. And that will be, and times d theta. And that will be our substitution that will get put in for dx. So this will be r cosine theta d theta. Cool. And now we keep going. So I've got 2, negative r to positive r. Oh, I almost forgot. In the last example, I wasn't dealing with an indefinite integral. I wasn't dealing with a definite integral. In this example, I'm dealing with a definite integral because I have boundaries of integration. So as I changed my dx to a value of d theta, and as I changed x to a value of r, I also need to change my limits of integration here as well too. So for the time being, I'm going to write those out until I get back to erase in the next step. Where will I do that? Do I have room over to the side? I think I don't. I'm going to have to erase over here. I don't want to erase my circle. Sorry, I didn't plan out my blackboard space as well as I should have. So we let x equal r sine theta. We also need to consider our changes to our limits of integration. So as x equals negative r, well, that means that r sine theta has to equal negative r, which means I'm looking for sine theta equaling -1. Because I just divide both sides by r. So now my angle of theta, which I'm integrating with respect to now, is going to go from -π/2. And that's because the first place where I see a sign of -1 is at -π/2. Now I could have written this as 3π/2, but I would be worried because then my first limit, that negative r was my first limit, would be at 3π/2, and my second limit is actually going to work out to be at π/2. So I would have to consider the order of those limits of integration switching if I didn't go to a negative value of theta. So that means my limit of integration of negative r is going to be actually -π/2. And likewise, when I'm doing r, I'll have x equal to r. So that means that r sine theta, which was my value for x, is going to be equal to r. Dividing leaves me with sine theta is equal to 1, and solving leaves me with it equal to π/2. And so now I know my upper limit of my limits of integration at π/2, and I'm happy because these work out to be in order. Boy, I'm glad I caught that misstep before we got too far. By the way, that's a very common misstep with definite integrals when you're doing any substitution, is forgetting to change your limits of integration. Okay, so now we have to do a little bit of math here to simplify this. As I had mentioned before, I'm going to common factor out an r squared. So this is going to be the square root of r squared, 1 minus sine squared theta, times r cosine theta d theta. Then next, I'm going to remove this r squared from the radical, which will combine it with this r. So this will be 2 negative π/2, π/2. So this will be r squared, root of 1 minus sine squared theta, cosine theta d theta. And we've gotten to a spot where we can now say, hey, that Pythagorean identity of 1 minus sine squared theta becoming cosine squared theta is going to allow me to eliminate my radical. So I'm going to have to unfortunately erase my limits of integration, and this step is going to move up over here. Clean off the board so it's easier to see. And so coming from here up to here, we're going to have my area of my circle being 2 times the integral from -π/2 to π/2 of the square root of cosine squared theta times cosine theta d theta. And now we just continue to move along. So we've got 2 times the integral of negative pi by 2, Cosine squared theta square root leaves me with cosine. Multiplying them leaves me with cosine squared theta d theta. That's fun. And now we have a situation where I think we're gonna want to use a u substitution, or actually, no, this is a situation where we did this by parts. So we can do this by parts, and we'll go ahead and do it by parts now. The integral of cosine squared theta is one that you maybe have memorized when we did our first integration by parts video, but I'm just going to work through it because, as I previously mentioned, I don't memorize a lot of these things either. So let's go ahead and evaluate this by parts. So we did our trig substitution, and our trig substitution accomplished our goal. We've taken something pretty complicated and we've gotten rid of the radical, and we're now down to something less complicated. And just like our previous example where we got to something we have to use by parts, it's very likely after you do a substitution that you'll have to do some other technique to get there, whether it's term by term integration or inspection or u substitution, or even in this case, integration by parts. So we'll set up to do integration by parts. And I'm actually just going to do this problem off to the side as an indefinite integral. So I'm going to ignore the 2, and I'm going to ignore the pi by 2 and negative pi by 2. And I'm just going to examine, okay, hold on a second. What is cosine squared theta d theta going to integrate to? So the integral of cosine squared theta d theta is going to be equal to cosine theta, and dv is going to be equal to cosine theta d theta. Deriving my u is going to get me negative. And of course, we have to be careful that we don't make a sign mistake. So I've got the negative sine theta d theta. And over here, I've got my integral of cosine is just my antiderivative, or sine theta. So now I can use my integration by parts formula. That's uv. So that's going to be sine theta cosine theta minus v du. So that's minus sine theta times sine theta d theta. And this is a negative. So this is what cosine squared theta is equal to, or the integral of cosine squared theta. So this is going to be sine theta cosine theta plus the integral of sine squared theta d theta. Now, fortunately, we can break up sine squared theta into, again, a Pythagorean identity. Strange how that's happening twice now. So we'll leave sine theta cosine theta alone, and we'll break this integral into 1 minus cosine theta, and that's still d theta. Now we can integrate this term by term, so we can integrate that 1. So this is going to be sine theta cosine theta plus the integral of 1 d theta is just theta minus the integral of cosine squared theta d theta. And that was all equal to, if you recall, the integral of cosine squared theta d theta. So I have 2 terms here of cosine squared theta d theta. So I'm going to add 1 to either side, leaving me with 2 of these. So 2 integral of cosine squared theta d thetas is equal to sine theta cosine theta plus theta. And my last step will be to divide everything by 2. So this will be over 2. Now previously, plus c, because we're at an indefinite integral. Previously, we had used the sine double angle formula to simplify sine theta cosine theta, so that our formula looked something like this. Would have looked like sine 2 theta over 4 plus theta over 2 plus c. And that's because this is 1/2 of sine 2 theta, because it doesn't have the coefficient of 2, and 1/2 divided by 2 is 1/4. So this will be what I'm going to substitute in for my evaluation of my integral. So I'm now going to have equals 2, the integral of negative pi by 2 to pi by 2. Sorry, I've integrated, so I'm going to change notation. This is going to be sine 2 theta over 4 plus theta over 2. I'm not going to add the plus c though because I'm dealing with a definite integral. I'm just going to remember that I have to evaluate it from both of my ends. So that was a fun little aside to do some integration by parts with trigonometry. And now we have to evaluate this. So I have to do 2 times, and I'll go through with pi by 2 first. So this is going to be sine of 2 times pi by 2 over 4 plus pi by 2 over 2. That's the first expression with pi by 2. Now I'll do the second expression with negative pi by 2. So it's minus sine of 2 times negative pi by 2 over 4 plus negative pi by 2 over 2. And so I've gone through with both my boundaries and remembering to subtract in between. Now sine of 2 pi by 2, if you cancel out your 2's, it's just the sine of pi. And of course the sine of pi happens all the way over here, and because sine is a vertical measure, the sine at pi is going to be 0. So this term is going to 0. By that exact same argument, this is going to be sine of negative pi, and sine of negative pi is going in the clockwise direction, is also going to work out to be 0. So that's going to be gone as well too, which is kind of nice. Hey, wait a second. Where did my r's go? I forgot some r's here, didn't I? Let's roll back the tape. I think I forgot r's when I went to bring this back up here. I believe I had an r squared sitting out front if we go back and look. This is frustrating. But fortunately r is a constant with respect to theta, so that means I can remove that constant from the integration. So I can just tuck that r squared in front and I don't have to erase a whole lot. So I'm quite happy with myself that I don't have to be too frustrated with this whole situation. I apologize. I think when I transcribed from here over, I forgot to bring my r squareds with me. I was too concerned about the upcoming integration by parts. So I'll simplify a little bit. This is 2r squared. Now this term, pi by 2 over 2, is going to be pi by 4. And this is going to be minus. Now minus. Now this is negative pi by 2 over 2, so that's negative pi by 4. And so I'm going to have 2r squared. Now pi by 4 minus negative pi by 4 is going to be 2 pi by 4s, or rather pi by 2s. Very nicely, those 2's cancel, leaving me with pi r squared. And so we just verified that the area of a circle. So that last video cut out right as we got to the point of canceling out our 2's and getting to pi r squared. And so there we've done it. We've gone ahead and verified the area of a circle is equal to pi r squared by expressing the upper border of the circle as a function of y, being y equals the root of r squared minus x squared, and then integrating underneath from the outer edge, negative the radius, to the inner edge, positive the radius, and doubling that whole product so that way we would get the entire circle. There were a couple of missteps, including my mistake with the sign, which I think I'll comically leave in the video because why not? And then also the forgetting of r squared when I transcribed back up. So I do apologize for the errors. There will be no outtakes today, but don't forget to hit like, subscribe, ring that notification bell, and check out the merch store for awesome chalk options.